Okay, so where we left off, we were talking about heat capacity constants for substances using the MCAT formula. And this example that we're about to do is exactly like something we're going to do in lab. Calorimetry, excuse me. The lab it's got three parts, which means it's kind of long. So I actually broke it up into 2 days because there's a chance we could get through all three parts in one day, but there's also a pretty good chance that we wouldn't. So because it's in parts, it's really easy to break up into two separate labs. But anyway, we're going to take 23.9 grams of iridium metal, and we're going to heat it to 89.7 degrees Celsius. Then we're going to put it into basically room temperature water that's in a calorimeter. Now, when you see calorimeter, the calorimeter is just an insulated container, but it's not a closed system. The calorimeter is just there to say that as the metal cools down and the water heats up, that we're not losing any energy to the surroundings. So what'll happen, and this is exactly how we're going to do it in lab, you're going to have a piece of metal, and it's going to be an unknown metal. It's going to be in a test tube. So this will be your metal. I'll just call it M for metal. It will be on the heating. You can either do Bunsen burner, hot water bath, or you can just inside a beaker of water, you can heat this on the hot plate. But you're going to, with some kind of heat source, you're going to heat the metal, and the temperature of the metal initially is going to be, in this case, 89.7 degrees Celsius. In lab, I tell you to get somewhere between 90 and 100. Then what'll happen is off to the side, you're going to have a calorimeter, which is just an insulated container. And in fact, it's just two styrofoam cups, but it works really well. And the calorimeter in this case just means that the energy exchange is confined to the system, right? We're not going to lose any energy to the surroundings. Now, inside that calorimeter is water. And the water initially, we are at 20 degrees Celsius. Oh, sorry, 20.1 degrees Celsius, 20.1 degrees Celsius. All right. Now, in order for us to understand any type of heat exchange, like we were talking about, we need the MCAT formula. So temperature is only part of the picture. We also need to know how much of the substance we have. So that metal mass, we have 23.9 grams. And the reason why we're heating it inside a test tube is because we want this to be dry. So when we transfer that metal into the calorimeter, it's not going to take any water with it because, of course, that water would be hot and it would also have part of this heat exchange problem. But we're going to heat it in an empty test tube so that it stays dry. So metal's going to be heated up, and we've got 23.9 grams of that metal, and we're going to heat it up right around to 90 degrees Celsius. Then we're going to add the metal to the water. And then what happens is, because we're in an insulator, a calorimeter, the metal is going to cool down and the water is going to heat up. And at some point, that temperature change is going to stop. So this is exactly how you're going to do it. You're going to have the metal in the test tube. It's going to be heated up. We can record that temperature just with a thermometer. We transfer that hot metal into the room temperature water in the calorimeter. And the calorimeter is going to have a lid. So just a styrofoam lid on it. And in that lid is going to be a hole. And in that hole, you're going to put the thermometer. So the thermometer is also going to just be sitting here in the solution. And you're going to see the temperature is going to go up right away because you just added a hot metal to it. So the final temperature goes up to 22.6 degrees Celsius. So that temperature happens because that temperature change happens because the metal cools down and the water heats up. So the question is, let's find the specific heat constant, the C, for the metal. And that's exactly what you're going to do in the lab. So there's two substances here, right? So there's kind of two things we have to calculate. We've got the iridium and we've got the water. So as it came up in the first session, will those heat capacity constants be given? So we're actually trying to solve for that for the iridium. So that's our unknown. But for the water, yes, it would have been given. So in this problem, it would have told us that the heat capacity for the water was 4.18 joule per gram degrees Celsius. Again, that's our constant for water. So that would be given. So there's two substances here. So this really is working like two MCAT formulas, right? This is the big thing here. The mass of the metal times the heat capacity constant for the metal times the change in temperature for the metal would be equal to the Q for the metal, right? That's our MCAT formula. But we also have mass of water, constant for the water, change in temperature for the water, and that would be equal to Q for the water, right? Two substances, two MCAT formulas. What's important and critical about this is that we understand that the Q, which is the heat from the metal, which is lost, it goes right to the water. So the Q for each of these is the same with one difference. It's just a negative sign, right? So if the water absorbs 100 joules of energy, that means the metal lost 100 joules of energy. If the water gained 200 kilojoules, then that means the metal lost 200 kilojoules. And that's because it's taking place in a calorimeter. So the calorimeter just basically says that this is insulated, right? And we're not going to lose any heat to the surroundings, that the metal will cool down, the water will heat up, but that exchange, that's the system, right? We don't have to worry about anything else. The system and the surroundings. Those are the two pieces. So we're trying to figure out the constant for the metal, the heat capacity constant for the metal. That's what we're trying to find. So if I look at my formulas, the C for the metal, that's my unknown, right? That's the one that I don't know yet going into this. But I know everything about the water. I know the mass of the water that was given to me at 20.0 grams. I know the heat capacity constant for water, the 4.18 joule per gram degree Celsius, and the temperature change for the water is just my final minus initial. So I have everything I need to know for the water. So part one, let's figure out the Q for the water. So mass of the water, 20.0 grams, constant 4.18 joule per gram degree Celsius, and then that delta T, the final temperature of 22.6 given to me in the problem, minus the initial temperature of 20.1 gave me a 2.5 degree Celsius temperature change. So if I multiply that out, 2.5 degrees was all we need. That was the only temperature change we saw for the water, not much. So it went up 2.5 degrees, multiply that by the 4.18 constant, and then multiply that by the fact that we had 20 grams. That means we had 209 joules of heat. This is absorbed by the water, right? Because the temperature went up. All right, so what that then tells me is that the Q for the metal is 209 joules, but instead it was released. And because it was released, that means it's now lost, right? So it's got a negative sign. So the big thing about these types of questions, when you have two substances exchanging heat, one is heating up, the other one's cooling down, is that this happens right here. The actual value for Q is the same for both. We're just changing the sign because for one, the heat is absorbed, so Q is positive. And then for the other one, the heat is released, so the Q is negative. That's the only difference, right? And let me just finish that sentence. This is what is released by the metal. The metal cooled down, it lost 209 joules. The water heated up, it absorbed 209 joules. So then what is our heat capacity constant for the metal? All right, so now the third part of this is if I'm going to find the constant for the metal, that would be equal to Q divided by mass and delta T. So we had a Q of negative 209 joules, mass of the metal, iridium, 23.9 grams. That was given to me back up here in the question. That's my mass of the metal. Oh, today's that day. All right, now the delta T for the metal. What's important is your delta T for the metal, you want to stick to the formula of final minus initial. We know the initial. The initial was 89.7 degrees. That's the starting temperature of the metal. When we put it into the water, it cooled down. When it gives you the final temperature of 22.6 degrees Celsius, right? That is for both the metal and the water, right? Because the metal will cool down, the water will heat up, and then at some point they're going to get to the same temperature. And then that's it. There's no more heat exchange, right? That's it. It stops. So when you get that final temperature, that's the same for both substances. So our change for the metal, we ended up at 22.6. We started at 89.7. So 22.6 minus 89.7 is obviously negative, but that's okay because our Q is negative. So those negatives are going to cancel out. So the metal cooled down by 67.1 degrees Celsius. So make sure you've got those two negatives in there because that's going to cancel out. So I've got negative 209 joules divided by the 23.9 mass, and then divided by the 67.1 negative temperature change. And just know your heat capacity constant always has to be a positive value, right? So the constants are always going to be positive. In this case, it would be 0.13 joule per gram degree Celsius. Now, the reason why I went with two significant figures is because if I go back up here to the change in temperature for the water, right? Because 22.6 and 20.0 is only 2.5 following the decimal place rule, this now becomes 2 sig figs. So at the end, my answer here needs to only have 2 sig figs. So we've got now our heat capacity constant for the metal. And if you remember the example we had in the part 1 video, that would have probably was lead, right? Lead was 0.128. So the big thing here is, since we know everything we need about the water, right? We went ahead and first started for the energy absorbed by the water, mass, C, delta T. Found out how much energy absorbed by the water. That was the exact same energy released by the metal. We just changed the sign. Then if I know my Q for the metal, and I know the mass of metal, and I know the change in temperature, okay, then I can then figure out my heat capacity constant. Change in temperature, again, your formula is always final minus initial. Change in temperature could be up or down, could be positive or negative. And that's what's going to decide Q, right? So if delta T is greater than 0, then Q is going to be greater than 0. If your change in temperature is negative, then your Q is going to be negative. Okay, so that's a big thing on the lab that we'll look at with these calculations, right? Mass can't be negative. Your heat capacity constant can't be negative. It's just your temperature could be negative, which could then make Q negative, right? If temperature is going down, you're losing energy. Okay, next example. This is going to start looking at thermochemical equations. It says we've got 23.6 grams of calcium chloride dissolved in water. The temperature goes up from 25 to 38.7 degrees Celsius. All right, so 23.6 grams of calcium chloride, change in temperature, final minus initial. We've got 38.7 is where it ended up. 25.0 is where it began. So we have a change in temperature of 13.7 degrees Celsius. If the heat capacity of the calorimeter combined is 1258 joule per gram degree Celsius, what is the enthalpy of this change in kilojoules per mole? So what I want to point out here is we've got the calorimeter, but notice it's just joule per Celsius. And a lot of times students are, again, looking for the grams in that, but that means that grams is not a part of this. So this calorimeter, this system, right? We put the calcium chloride in that. Obviously, there was water in there. That 1258 already includes the mass of the water, right? So we know that if the water temperature goes up, we know because of the 4.18, that's already been factored in. So this particular system, the 1258 joule per degree Celsius, the mass of water has already been factored into that, which is why it's such a large constant, right? So because the constant was given in joules per degree Celsius, that means your mass is not needed. Now you might be saying, but I have mass of calcium chloride, right? But that's not what's absorbing the heat. It's this calorimeter that's absorbing the heat. So all I'm going to do is to figure out the Q for the calorimeter, I'm going to take that constant and multiply it by delta T. So we've got 1258 joule per degree Celsius, and we had a change in temperature of 13.7 degrees Celsius. So I'm going to take 1258 times 13.7, and I get 17,235 joules. Okay, we'll worry about sig figs here at the end. All right, now that was absorbed by the calorimeter. All right, now again, that means that the Q for the reaction, right? Where did that heat come from? So the calcium chloride, anybody who ever has to add calcium to their pool, they may know this. It's highly exothermic. You'll feel the water get warm when that calcium dissolves. So the heat, not calcium metal, by the way, just in case anybody's like, what? It's the salt. So we've got 17,000 joules that were released from that reaction, which in this case is just a physical change. We're just dissolving the calcium chloride. So the reaction here, this is dissolving the calcium chloride. And that released 17,235 joules, right? So again, same thing, same concept of what we had earlier. The heat absorbed by the calorimeter is the heat released by the reaction. So this is another thing we're going to look at in our lab, that we're going to have the amount of energy absorbed, could have been by the water, but in this case, it's in the calorimeter, the system, the sort of closed system. And then that means that is the energy released by dissolving the calcium chloride. So a thermochemical equation, which is kind of what this is looking for, is it says, okay, if we take the calcium chloride and we dissolve it into calcium ions and chloride ions, the energy that we released here is 17,235 joules. And it was released. So that means that this is an exothermic reaction. And we'll talk more about that on the next page. The energy is being released by this solution process, and that energy is then absorbed by the calorimeter. So that makes this, again, a negative energy. Now, that energy is based on using 23.6 grams of calcium chloride. So something, you know, conceptually, we know that if we'd used 50 grams, we would have gotten even more energy out, right? It would have even been more negative. If we had used less grams, we would have gotten less energy out. But that's the amount of energy we got from dissolving 23.6 grams. So this is what a thermochemical equation is that you'll have the chemical equation, and then you'll be given the energy that's either absorbed or released by that reaction. And because the energy is being released by the process, that's why the sign again is negative. All right. So negative means exothermic, but we'll get to that on the next page. Now, as you might imagine, thermochemical equations, they are typically not given in terms of grams. They're going to be given in terms of moles, as you might imagine. So what I'm going to do here is convert the grams of calcium chloride to moles of calcium chloride. So calcium 40.08, chlorine times 2, 70.9. If I add the two together, I get 110.98 for the molar mass. So 23.6 divided by that molar mass. Hold on. 23.6 divided by 110.98. What I get here is 0.213 moles of calcium chloride. So I got this much energy released for this many moles of calcium chloride. And what it wants me to have is kilojoules per mole. So how do I change this to kilojoules per mole? So what I'm going to do here is first joules to kilojoules. all I'm going to do is divide that by 1,000 and I get negative 17.2 kilojoules. Now I'll start rounding it to 3 sig figs, which is what it should be for the delta T. So negative 17.2 kilojoules for using 0.213 moles. All right, well, what would it then be in kilojoules per 1 mole? So it's basically just a ratio. So at the very end, what I'll have, and I'm going to take this over here to the side, is I would have negative 17.2 kilojoules released for 0.213 moles of calcium chloride. And so what I get here in kilojoules per mole is negative 80.8 kilojoules per mole. So a thermochemical equation, it's a chemical equation, so we can rewrite that chemical equation with a thermo component, which means that we're going to have what's called the enthalpy, delta H, also attached. Oops, there's supposed to be a point there. All right, so negative 80.8 to repeat what we got over there. Now, it typically won't say kilojoules per mole because when it's attached to the equation, it's implied that it's per mole of the calcium chloride. So this right here, that would be your thermochemical equation. Basically, it's a chemical equation with the thermo attached, like the energy temperature part. So the enthalpy, right? This is the enthalpy of the reaction. And what we can start doing is calculations with this to say, okay, well, let's say we had 1,000 moles of calcium chloride. How much energy would we get, right? We can start doing that. That's what's coming. So that is a thermochemical equation. Just to recap it, we first used the calorimeter information and the delta T to figure out how much energy was absorbed by the calorimeter. Just like we talked about in the last example, energy absorbed by that container, right? The calorimeter was the energy released by the reaction. In this case, just the physical change of dissolving. Now, if that's the amount of energy I got for 23.6 grams, once I convert that to moles, I really had about 0.213 moles. So if I got that much energy for that many moles, once I just change the numbers, right? Divide energy divided by moles, making sure energy is in kilojoules. This would be the amount of kilojoules I would get for every 1 mole. So now I have a thermochemical equation. So if your delta H is negative, right? If delta H is less than 0, then that means you have what is called an exothermic reaction. And that means the energy or the heat exits the reaction, right? So what'll happen is the exothermic reaction will always cause the surroundings to heat up, right? Because there's an energy exchange. This system, the dissolving system, is releasing energy. So the surroundings are going to heat up, the calorimeter. So in terms of the equation, which one to use, whether it's MC delta T or just C delta T, the units are going to tell you that the unit here didn't have mass in it, no grams. So you know you don't need grams for the calorimeter. If it's just joule per degree Celsius, then all you need is the degree Celsius, the delta T. That's how you know whether you're using MC delta T or just C delta T. It also tells you that you've got the calorimeter, so you know that this whole thing combined together, this piece, rather than just like water or lead, right? So it's not a substance specific constant, it's this whole contraption constant. All right, so if delta H is negative, that means it is an exothermic process. That means the energy exits, which is going to cause the surroundings will heat up. All right. So the system is releasing energy, the surroundings is going up. Do you find enthalpy the same way for substances? So if you're just heating substances, there really isn't an enthalpy with that. If you're just heating up metal, enthalpy is only for a reaction. So if you're only heating up a metal, then it's just the MCAT formula. But if you're doing any kind of reaction, if it's dissolving, right, just a physical change or a chemical change, that's when you can find enthalpy. So enthalpy is always like it's attached to a system, some kind of change. But you wouldn't do an enthalpy for a specific substance because there's nothing happening with the substance, right? That's just an MCAT formula. But if you're dissolving the substance or reacting the substance, that's when you can find your enthalpy. All right, good questions. All right, then endothermic versus exothermic. So we talked a little bit about exothermic. So if your delta H is negative, you know it is an exothermic process. And that means your heat energy exits. That's how I remembered it. Exo exits. And that's going to cause the surroundings, like if we're doing this in a test tube, the test tube is going to start to feel warm. If it's endothermic, when I kind of thought of, okay, delta H, if it's greater than 0, positive, then we know endothermic. And I remembered it as energy or heat flows in to the process, right? Meaning it is absorbed. Well, it's absorbed from the surroundings. So that means your surroundings are going to cool down. They're going to feel cold to the touch. All right. So surrounding temperature is going to cool down. Come back. There we go. Okay. So if your delta H is negative, that means this process is exothermic. Energy exits. Your surroundings are going to heat up. If it's endothermic, delta H is greater than 0, positive. That means energy is required for that reaction to go. It's absorbed. And the only thing that can supply that energy is the surroundings. So if you're doing a reaction in a test tube, your test tube's going to feel cold because energy is getting sucked into the reaction, right? So if we look at this, I did that backwards. Sorry. This right here is supposed to be here. Endothermic versus exothermic. Exothermic we had up here on this page. So you may want to adjust that. So exothermic, delta H negative, less than 0, energy exits, right? And the surroundings are going to start to feel warm to the touch. If it's endothermic, heat goes in. Now there's an energy diagram here. So if we just look at energy and we look at progress, like we talked about before the reaction, there is a certain amount of stored chemical energy. Focus. Okay, so stored chemical energy in the molecules. So this is where we're starting out in the reaction. These are our reactants. When you go through any kind of chemical change, you have to increase energy, has to go in to break up bonds. And then energy is released as you form new bonds. If it's exothermic, you still have to have that initial uphill climb, but where you end up is much lower than where you began. So based on where we started to where we finished, energy exited, it left, it was released, right? If it's an endothermic, so this right here, this is exo. If it's endothermic, it's the opposite. If I'm looking at energy and I'm looking at your reaction progress, again, you'd start out at some baseline stored chemical energy. You still have your uphill battle. That's called the activation energy. And that is to break bonds, right? But then as you form new bonds and the molecules then restabilize, you release energy. But in an endothermic process, where you end up is at a higher energy than where you began. So now if I'm looking at this net, right, energy had to go into the process. The amount of energy absorbed versus released, overall more was absorbed. In exothermic, more gets released than was taken in. But either way, you've got to get past something called the activation energy. And that's actually something you look much more at with Chem 2. Sorry about doing those sort of backwards. All right. Now, then this example here, we want to know the enthalpy for the reaction if I use 3/2 oxygen to make 1 ozone, O3. And I'm given a thermochemical equation. It says for 3 moles of O2 to make 2 moles of ozone, 285.4 kilojoules is absorbed, right? It's positive. So that tells me that this is an endothermic process. So energy is absorbed. So this is good. Great. We want oxygen, so um, we're not going to consume all of our oxygen to make ozone. So it can happen, but energy has to go. So typically if something's endothermic, it's not quite as spontaneous as something that's exothermic, but there's factors that you learn about in Chem 2 for that. So what this question is saying is, okay, let's say instead we had 3/2 oxygen making just one ozone. And now let's figure out what the delta H would be for that. So if I look at those two chemical equations, what I notice is the only difference between the two, I've got oxygen making ozone. Instead of 3, I have 1.5. And instead of 2, I've got 1. So all I'm looking at is from the first equation to the second equation, I basically am taking half of it, right? So instead of 3 oxygens, I do 3/2. Instead of 2, I just do 1. So if I absorb 285 kilojoules for using 3 moles of oxygen, if I'm going to use half of that, I'm going to require half of that energy. So this is going to come back in a little bit when we do Hess's law, that if I use less O2, then I need less energy, right? And so if I'm cutting my O2 in half, then I'm going to cut my energy in half. So the 285.4, if I divide that by 2, what I get here is a delta H for this new reaction of 142.7. Okay, so we just cut delta H in half because we cut the reaction in half. All right, and we're going to come back to that in Hess's law. If I change it, and let's say, this is another thing that's going to come up. Let's say we had 2 ozone creating, it's going to drive me bonkers today. I'm trying not to get bonkered out. 3 O2. All right, so what I did now between my starting equation and to my second equation here in purple, I have 3 oxygens on the reactant side. I now put that on the product side. The 2 ozones on the product side, I now have on the reactant side. So all I did here is I reversed the equation. So if it's all about kind of thinking about this diagram, right? This was an endothermic reaction because it's a positive delta H. So if I'm going up, right, and then getting past the activation energy, then releasing energy, and overall net, I need 285.4 kilojoules. Well, if I reverse it, I'm just going to go the other way. And so now my products are my reactants, and my reactants are my products. So if I'm thinking about going the other way, because I've flipped the reaction, so I'm going in the opposite direction. Now, instead of going uphill, it's a downhill. So if it requires 285 kilojoules to go this way, if I go the other way, it's going to release. So if you reverse the sign, you just change the sign of your delta H, right? So if I just flip the equation, I change the sign for delta H. This is all like really intuitive. It makes it really easy. If I multiply the equation by a certain number, then I multiply delta H by that number. If I reverse it, I just change the sign. All right, so this is going to come back when we do Hess's law. Before we get to Hess's law, now let's start thinking about some thermochemical equations and how to use it in stoichiometry. So we have a reaction here of hydrogen with chlorine to make hydrogen chloride. Now, normally if it were be in water, it'd be hydrochloric acid, but because it's not in water, it's actually just hydrogen chloride. But anyway, we have negative 184.6 kilojoules. All right, so again, just getting used to it, that means this is exothermic, energy is released. What is the enthalpy change when 12.8 grams of hydrogen reacts with excess chlorine? Good, so this is not a limiting reactant problem. And it doesn't mention anything about HCl, so really what it's asking is, we want to know how much energy. So the way I kind of think about this is if I rewrite my thermochemical equation, I've got my hydrogen, 12.8 grams of it, reacting with chlorine, which is just excess. We're making hydrogen chloride. And because this is an exothermic reaction, that means that energy, heat energy is released, right? It's going to be on the product side. So basically, I've got over here my heat. It's being released. All right, heat being released means it is a product. So the question is, if I use 12.8 grams of hydrogen, how much heat am I going to produce? Well, I know that based on this equation, that I would get 184.6 kilojoules if I use 1 mole of hydrogen. So I can use that relationship to then figure out, okay, well, how many moles of hydrogen do I have? And then how much energy? So your delta H, this is something we haven't done yet with stoichiometry. This is actually your conversion factor, right? And that conversion factor is going to help us relate moles and energy. And what this tells me is I have negative 184.6 kilojoules released every time I react 1 mole of hydrogen. And in that thermochemical equation, you can relate it to any one of the substances that you're looking at. I know I get 184.6 kilojoules released every time I react 1 mole of hydrogen. I also get that same energy by reacting 1 mole of chlorine, right? Assuming hydrogen would be excess there. But if I make 2 moles of HCl, I get the 184.6. So if I were looking at HCl, okay, so that I'm not doing it here, but if I was, I'd get negative 184.6 kilojoules for every 2 moles of HCl. So you can take your delta H and relate it to any of the substances in that chemical equation. And so in this case, because we're looking at hydrogen, that molar coefficient just has a 1. But this is a conversion factor. So we're going to use that in the parentheses. So we're going to start with our 12.8 grams of hydrogen, molar mass, 1 mole of hydrogen, 2.02 grams. And then this is our new conversion step for thermochem. Negative 184.6 kilojoules is released for every 1 mole of H2. All right, and that'll give me my enthalpy. Enthalpy just meaning your heat, right? Your heat change, your energy, joules or kilojoules. So I'll take 12.8 divided by 2.02. Basically, we have a little over 6 moles of hydrogen. And if I get 184.6 kilojoules for every 1 mole of hydrogen, now that I have about 6, how much energy am I going to get? It's going to be a lot. So when I multiply everything through, hold on one second, 12.8 divided by 2.02, I'm just typing it in again. I get negative 1,170 kilojoules. So that would be the amount of energy released by burning 12.8 grams of hydrogen, assuming again that we had excess chlorine. And since chlorine wasn't mentioned in the question, that assumption sticks, right? We don't have to worry about the chlorine. So a thermochemical equation allows us to do a new calculation here, which is we can look at the energy of that change, whether it's a physical change like the calcium chloride dissolving, or it's an actual chemical change like this combination reaction. But that delta H allows us to say, okay, well, we get this much energy based on 1 mole, 2 moles. So if we have more than that or less than that, how much energy should we get? But this is our constant. So it'll be our conversion factor. So delta H is now a conversion factor in our chemical equations, our thermochemical equations. So next one's going to be slightly more complicated. We want to know the volume of methane. I would tell you that's CH4. So we're looking at volume. We are at 25 degrees Celsius and 745 torr. So this is sounding and feeling like a gas loss problem. And we have excess oxygen so that we just don't have to worry about this being a limiting reactant problem. And we want to release 1 times 10 to the 6 kilojoules of heat. All right, so this is our heat total that we want to produce. And we have a conversion factor, right? Which is the delta H says, I'll get 890.3 kilojoules released for every 1 mole of methane. I'm looking to get 1 times 10 to the 6 kilojoules released. So now how many moles of methane do I actually have to get? So in this one, we're looking for the CH4, excuse me, and we are given that we had 1.00 times 10 to the 6 kilojoules. That's how much we want. That's our target. So since we have energy, that's going to act as our A, and the methane is going to act as our B. It's where we're headed. So we start with our energy, 1.00 times 10 to the 6 kilojoules released. Based on my delta H, I get negative 890.3 kilojoules released every time I react 1 mole of CH4. Because this is a gas laws problem, right? We see temperature, pressure, we see gas laws. We're going to think about using Pivnert. So this will tell us our moles that we need for the methane. And what I get here is 1123 moles of CH4. So what I know is 1 mole of methane will release 890.3 kilojoules. I want 1 times 10 to the 6 kilojoules, which is a lot, right? So I need 1123 moles of methane, right? But if I want to relate that to volume, volume would be nRT over P. So I want 1123 moles, R 0.08 Temperature was 25 degrees Celsius, but that would become 298 after you convert it to Kelvin. And the pressure was 745 torr, but if I divide that by 760, it's 0.980 ATM. All right, so let me just write that over there. Let me do it up here, actually. Pressure would be 745 divided by 760 to convert, so 0.980 ATM. All right, so I've got my 1123 moles times 0.08 206, then multiplying that by 298, and then dividing that by my pressure of 0.980. And my volume here is 28022 liters. All right, and then we got to go back and think about significant figures, which is going to be 3 here. And if I'm looking to get that to 3 sig figs, the only way for me to do it is to do scientific notation, right? If I do 28,000, so 28000, that's only 2 sig figs. If I do 28020, that's 4. So there's no way to do this except to say 2.80 times 10 to the 4th. We're moving it 1, 2, 3, 4 spots. And that would be my volume with 3 sig figs. That would be the volume of methane I would have to consume in this combustion reaction in order to get that much energy, 1 times 10 to the 6 released kilojoules. Okay. All right, let's do one more here before we start talking about something else. Question says, what volume of the HCl? We again, looking like gas laws, 125 is 398 Kelvin, pressure 0.971. Anytime you've got pressure, you know it's a gas loss problem. And we are producing 1575 kilojoules of heat. All right, and again, we've got our delta H value. So we know that we have produced, right, 1575 kilojoules. So again, we know how much heat, that's going to be our A. The volume of HCl is going to be our B, just like we did in the last example. So we know we get negative 185 kilojoules every time we produce 2 moles of HCl. This time, though, we want 1575 released. So again, it's going to be negative. So now how much HCl do we need? Well, we know it's going to be more than 2 moles. So we start with our energy, negative 1575 kilojoules. The thermochemical equation, right? This is our delta H. We get negative 185 kilojoules. And this is written the way that this equation is set up. So I get the negative 185 every time I produce 2 moles of HCl. So just make very sure that when you use that delta H as your conversion factor, that whatever substance it is you're looking at in the chemical equation, that molar coefficient is part of that conversion factor. Okay, like in the last example, it was just 1 mole of methane. There was no coefficient in front of the methane. So it was just 1 mole of methane. But on this one, because the equation says that, well, you get 2 moles of HCl and you get 185 kilojoules released. So we have to make sure that that's the conversion. Since we're looking at HCl, we've got to be making sure to factor in that there's 2 moles every time we get 185 kilojoules released. So this would be my N, just like we did on the last example. So I'm going to take the 1575 negative, divided it by 185 negative, and then multiply that by 2. And this is 17.03 moles of HCl. Volume would be nRT over P. So we have 17.03 moles, R 0.08206, temperature converted to Kelvin 398, and pressure in atmospheres 0.971. So the volume of HCl that I would produce at that temperature and that pressure in order to get 1,575 kilojoules released, I would have to also be producing 573 liters of HCl. All right. So we're combining 2 chapters. We've got the chapter 6 gas laws, stoichiometry. We know we go through Pivnert. And now we're doing the chapter 7 thermochemical. And the reason why the 1575 was negative is because it told us that the energy was released. So that means it's going to be a negative energy. It's going to be on the product side. And if you missed the negative on the 1575, just make sure when you get moles, moles can't be negative. So these 2 negatives should cancel out. But if you miss it here, and then you end up thinking, well, moles can't be negative, just take the absolute value, just get rid of the sign. But just because it's released, it should technically be negative, which makes sense because then it's going to cancel out with the negative 185. But moles has to be a positive number. Volume has to be a positive number, right? Delta T can be negative. Energy can be negative. But volume, pressure, temperature, moles, that all has to be positive value. All right. So chapter 6, chapter 7. Oh, okay. This is going to kill me today. All right. One more topic, actually 2, but I think we're only going to get to one more today. And that is Hess's law. And we already started thinking about that with the oxygen ozone equation we saw earlier. So what'll happen here is we're going to revisit a couple of things we looked at. If you multiply through a chemical equation by a certain n, like we did with the 1/2, then you multiply your delta H by that same 1/2 or whatever it is. If you reverse the chemical equation, you just change the sign of the delta H. And then the last one that we haven't looked at yet is if you add 2 reactions together, you add the 2 delta H's together. So it's very intuitive, right? If you multiply the equation by a certain number, you multiply the delta H by the same number. If you reverse the equation, you reverse the sign of delta H. If you add equations together, you add the delta H's. So Hess's law, I have to say, my experience with Hess's law is that students, for some, it seems really simple and straightforward. And then for some, it doesn't go well. And I haven't figured out really why. I think it's because Hess's law, a lot of times it's an all or nothing question. And you may have made a tiny mistake and it throws off your answer, but I don't necessarily see that. So, show as much work for me as you can, because to me, Hess's law, when I learned these, I was like, oh, I like these. These are kind of fun, kind of easy. So what'll happen is like you'll be given thermochemical equations, and then you're going to be asked for the thermo piece, right? The enthalpy for an equation. So like you have these givens and then you're looking for the delta H for another one. So we want to know the delta H for the reaction of methane with oxygen, which makes CO and carbon monoxide and water, right? Combustion. We want to know the enthalpy for this equation. And we have a couple down here. These are the given. So we've got methane plus oxygen and to make CO2 and water. That one we're more familiar with. And then we've got a reaction of CO with oxygen to make CO2. So the idea is that when you have these thermochemical equations, the delta H is based on breaking bonds and forming new bonds and the certain amount of stored chemical energy. So if I look at the two given equations and I find what I call the discrete substances, it's a substance that only appears in one of those equations, then I can kind of try to figure out how to make this work. The goal is we're going to take the given equations, and I'll mark those as number 1 and number 2, and we're going to manipulate them to where they start to look like our target equation. So the target equation is the one that we don't know what it is. We don't know the delta H yet. So what do I look for? The discrete substances. What I mean by that is oxygen would be a terrible place to start because it's in both of the given equations. So I don't want to look at oxygen because I don't know where to get it from. The carbon monoxide would be okay because it only comes from equation 1. The water would be okay because it's only present in equation 2. And the methane would be okay because it's also in equation 2. I'm just going to use the methane because it's the first thing that's listed. All right, so when I look at the methane is only in equation number 2. So I'm going to ask myself, what do I need to do to equation 2? You only have 2 possibilities. You have to look at the coefficient in front, and you have to look at if it's on the right side of the equation. So methane is a reactant, and in my given equation, it's a reactant. So I'm not going to flip the equation or reverse it. It's going to stay reactant, reactant. What I notice though is that in equation 2, I only have 1 methane, and in my target, I need 2 methanes. So that means I'm going to multiply 2 times that second equation. So I'm going to rewrite it. Instead of 1 methane, I would have 2. Instead of 2 oxygens, I would have 4. Instead of 1 carbon dioxide, I would have 2. And instead of 2 waters, I would now have 4. So what I did is I took equation 2 and I multiplied everything through by 2. So 2 methanes, 4 oxygens, 2 carbon dioxides, 4 waters. Since I multiplied the equation by 2, I'm going to multiply the delta H by 2. So delta H now becomes 2 times negative 890.3. All right, so let me go ahead and get that answer. 890.3 times 2 is negative 1780.6. All right, so that's the first one. Now let's look at the second one. All right, now the other thing we could look at here is in this first equation, what I notice is the carbon monoxide. CO2, nope, not in there. We're not going to look at O2, right? Because it's in both of these. We just want the discrete. So if I look at the carbon monoxide, I'm only going to be looking at equation 1. So what do I need to do to equation 1? First thing is carbon monoxide on the right side? Meaning it's on the product side in my target, but it's on the reactant side in my given. So I'm going to have to take my given equation and flip it. So for equation 1, I'm going to flip it. Then the other thing I look at again is the coefficient. Those are the only 2 things you have to look at. Do I flip it? What's the coefficient? In my given equation, coefficient of 1. In my target, the one I need it to be a 2. So I need to go from a 1 to a 2. So again, I'm going to multiply it by 2. So I got to do 2 things here. I'm going to flip the equation and I'm going to multiply it by 2. So the product CO2 becomes the reactant CO2. The coefficient of 1 now becomes a coefficient of 2. Then changing it, the carbon monoxide reactant now becomes the carbon monoxide product, and the 1 in front now becomes a 2. And then the oxygen reactant now becomes a product, but the 1/2 times 2 becomes a 1. All right, and now what's happened to that delta H? Well, I would take that negative 283.0, and because I flipped the equation, I have to change the sign. So now it becomes positive, and I multiplied it by 2. So I've got to take positive 283 times 2, and I get positive 566. All right, now what am I looking at? I'm going to take my two equations now, and I'm going to add them together. And if you want to write this out the long way, you certainly can. Or I can show you how it'll just simplify. But I'm going to go ahead and write it the long way. So the long way is everything on the reactant side I'm going to rewrite. So I've got 2CH4 plus 4O2 plus 2CO2, right? So everything on the reactant side, I line up my arrows to make it easy. So everything on the reactant side is still there. Okay. 2 methanes, 4 oxygens, 2 CO2s, all on the reactant side. Then on the product side, adding this all together, I've got 2 CO2s, 2 COs, 4 water, and an oxygen. Okay, so all 4 things on the product side are all still there. When you simplify, anything that looks exactly the same on both sides is going to cancel out. So 2 CO2 and 2 CO2, reactant and product, go away. The methane doesn't simplify. The carbon monoxide doesn't simplify the water, but the oxygen, I can take away 1 oxygen, and then that 4 becomes a 3. We just subtracted 1 oxygen from both sides. If you don't want to have to write everything out, just look, anything that's the same on both sides of the arrow is going to cancel. And so the oxygen here, one of them now becomes a 3. So what I have left is my target equation. What I have left is the 2 CH4s plus the now 3 O2s to make the 2 COs and the 4 H2O, right? And that was the target equation I was looking for. Now, what do I do to delta H? I'm going to take my adjusted delta H for both of those equations, and I'm going to add those together. So because I added the 2 equations, I'm going to add the delta H's. So negative 1780.6 added to a positive 566. And what I get there is now the thermochemical equation. My delta H here is negative 1214.6 kilojoules. All right, so delta H now, come back. There we go. Negative 1214.6 kilojoules. So what happens in Hess's law is you're given known equations, known thermochemical equations, and you want to know the delta H for a different equation. It's similar, but not quite the same. What you have to figure out is, okay, how do I move around these given equations to end up looking like my target? There's only 2 things that you can look at. You can look at what should I multiply by and should I reverse the equation? Those are the only 2 things you have to ask yourself. So look for the discrete substances, right? Something in the target equation that's only found in one of the other equations. So methane, is it on the right side? Yep, reactant. Does it have the right coefficient in front? Nope. I got to multiply by 2, so that means I got to multiply delta H by 2. Then I looked at the carbon monoxide. You only have to look at 2 things because there's only 2 equations here. Carbon monoxide in my target, then look at carbon monoxide in equation 1. Number 1, I need to flip it. It needs to be on the product side. And then number 2, I need it to have a coefficient of 2 in front. So I'm going to take my given equation and flip it and multiply by 2. That means I'm going to take my delta H, change the sign, and multiply by 2. Once I add the two equations together, I should get my target equation if I did it correctly. And when you add your equations together, you just add your delta H values, and that'll give you your delta H for that new equation. So we found that the delta H here is negative 1214.6 kilojoules. That's our delta H for that target equation. All right. So that's a great place for me to stop for today because we got another example to do when we come back on Thursday. We're also going to look at enthalpies of formation, and then we'll get started with chapter 8. And chapter 8 is a shorter chapter. So that's why I know we seem like we're a little bit behind on the calendar, but we've got enough time on Thursday to make up for it. All right. So that also means, though, that your test 2 is coming up next week. It always moves so quickly. So Thursday, we're going to do chapter 8. And then next week, Tuesday, we're going to review. And next week, Thursday, it's going to be time for test 2 already. So I hope you have a great rest of your day. I'll see you back on Thursday.